So welcome everybody to the last session, unfortunately. But we're going to have a series of talk about choreographies, library level choreographies and embeddings. We're starting with Shun, who's going to present ChoRus, or ChoRus, ChoRus.
All right, so can everyone hear me okay? Okay, so hello. So today I will talk about ChoRus, which is a Rust library for doing choreographic programming. My name is Shun, Kashiwa, and this is a joint work with my advisor, Lindsey, Kuper at UC Santa Cruz. So this is a choreographic programming workshop, so I assume everyone here is familiar with the idea of choreographic programming. I am interested in doing choreographic programming at the library level. And by which I mean we express choreographies as programs in an existing host programming language. And this is as opposed to choreographic programming languages like being a standalone and has its own syntax and semantics. Library level choreographic programming enjoys the same advantages to embedded domain specific languages. So users don't need to learn new syntax. It can be installed just like any other host language library. It works well with existing host language program. And you can use any host language developer tools like IDEs and debuggers. Haskell was the first to introduce the idea of library level choreographic programming. And here is a sample choreography in Haskell. So Haskell is a Haskell library. And we express choreographies as computation in this choreo monad. And inside this choreo monad, you could use choreographic operators like locally and squiggle arrow that represents communication. So Haskell brought choreographic programming to Haskell, which led me to this question of, what about other languages? Like we have a lot of programming languages. Can we do choreographic programming in those languages? And well, of course, we can do the same in any tooling complete language. But doing it right turns out to be non-trivial. And this is largely due to the fact that Haskell's design is tightly coupled with Haskell and its features around monads. So if we directly translate Haskell into a language without the do notation, basically what you would have is you simulate monads with method chain. So you have something, dot, and then blah, dots, and then blah. And that's not how you write programs in those languages. So I got interested in this question of can we design choreographic programming library that is developer-friendly in those other languages. And ChoRus is my attempt to that challenge. So it is a library in the Rust programming language. It is distributed as a cargo package, so it can be installed on any Rust project. And it implements endpoint projection as a well-known software engineering technique, dependency injection. So in this talk, I'll first talk about how to use ChoRus as a user and how you can write choreographic code in Rust. Then I will discuss its implementation and especially how ChoRus does endpoint projection. And finally, I will briefly talk about two ChoRus-specific features, how ChoRus encodes location set at the type level and choreographic enclave operator. So let's start writing a choreography in Rust. And obviously, we're going to use the bookseller protocol. So in the bookseller protocol, there are two locations. And the first thing we need is to define those locations. So here, so ChoRus represents each location as a distinct type. So we define two empty structs, one called the buyer and the other called the seller. We also derive this choreography location trait so that the library can compare two locations for equality during the endpoint projection. Next, we define a choreography. So we create another empty struct called bookseller choreography, and this is going to be the choreography. And we implement this choreography trait on this empty struct. In order for something to be a choreography, you need to provide two things. First is this associated type L that represents a set of locations involved in this choreography. So in this case, we use this special macro location set to create a type level encoding of location set that has both seller and buyer in it. Then we also need to provide this run method, and this is where we are going to write the actual choreographic code. So the first thing you need to do in this protocol is to get the title of the book that the buyer wants to purchase. And we assume the terminal environment, so we want to read a line from the standard input on the buyer location. In order to do such a local computation, we use the locally operator, which is right here. And we specify the location of the computation, which is buyer. And as the second argument, we provide the local computation as a closure. So inside this closure, we are just using the standard Rust code and reading a standard input one line. Because this closure returns a string, this locally operator returns a located string. So this is a located value. And where does it locate? It's located on the buyer. OK, so that's the first step. And the second step is to move this data on the buyer to the seller. And for that, we use this com operator. So in this line, we're saying move from buyer to seller, this title at buyer, which we just obtained. And as a result, we get located. It's still a string, but now it's located at the seller location. OK, so once we move the data, the seller will be able to access the value inside its local computation. So when you do a local computation, we provide this un object, which we call the unwrapper. And this provides a capability to unwrap a located value into normal Rust values. So inside, we can use this unwrap method and provide this title at seller. And you can get the regular Rust string out of it. And you can use it whatever you want. So in this case, we are using this get book price that might do maybe a database lookup. And it'll return an integer. That's the price of the book. OK, so we can use the same com operator to send the price back to the buyer. And buyer can compare its price against their budget to see if they can actually purchase the book. OK, so now we have a decision. And this is located at the buyer. And I omitted the type, but it's located Boolean at buyer. So now we want to make a branch out of this located value. And in ChoRus, to do so, we use the third choreographic operator called broadcast. So as its name suggests, it broadcasts a located value into all locations. So it's making it no longer a located value, and it just returns a regular Boolean in this case. And because it returns a regular Boolean, we could use any of the Rust built-in control flow constructs to make a branch. So in this case, we want to use the if statement. So if the buyer decides to buy the book, we can do more communication about the delivery date. And if not, we can just print the buyer cannot buy the book locally on the buyer. So this is the complete choreography in ChoRus. And to execute this choreography, we need to take two more steps. The first is to define what's called transport. And transport describes how two locations should communicate with each other. ChoRus provides the built-in HTTP transport. So if you provide the host name and the port number, you'll be able to use HTTP as a backend. You can also create your own custom transport, and you can use protocol of your choice as an underlying mechanism. So that's the first step. And the second step is to actually do the endpoint projection. You need to instantiate this projector object providing the transport. And you call EPP and RAM method and provide the choreography. So let's see how it works in action. So I am running the seller on the right and buyer on the left. And obviously, I want to buy the book Introduction to Choreographies. And it says, apparently, it's affordable. And the book will be delivered next week. Isn't that great? OK, so before I move on, I want to show one more example, which is this choreographic tic-tac-toe written in Rust. So this protocol involves two locations, player X and player O. And inside this Rust built-in loop, you can think of it as a while true. They take turns, make moves, and broadcast until the game is done. So and here is how it works. So this example has an AI mode that implements the minimax algorithm. So me on the left is competing against the AI on the right I want to point out two things. So first, it might be hard to see on the screen, but some of the letters are shown in color. And to do that, I could just use the Rust library to print text in color. Because we're doing everything at the library level, you can use whatever Rust code in a local computation. Also, I'm not really an AI person, so I don't really memorize how to implement the minimax algorithm. GitHub Copilot was able to write code for me because obviously it's a library level, and large language models are familiar with the syntax and syntax of the Rust and also how algorithm works. So I think these illustrate the advantages of doing it at the library level. OK, so let's shift our focus to how the library is implemented, and especially how ChoRus performs endpoint projection. The key observation of library level CP is that the behaviors choreographic operators change depending on the location to which you're projecting. So take locally operator, for example. It takes the location and computation. So what should this operator do? Well, it depends on the projection target. If the projection target is the same as the specified location, it should do the computation. Otherwise, this line should be treated as null up. Similarly, for com operator, if the projection target is the sender, you should do the send. If it's a receiver, you should do the receive, and null up otherwise. So behavior of these operators depending on the current projection target. And we can change the operator's behavior if we inject different implementations of choreographic operators into a choreography that's written in terms of an abstract interface. So let's get back to the bookstore choreography. And you notice that we used com and locally those choreographic operators on this ob object. And in this line, we're saying this ob object implements this choreop trait. Or if you're familiar with Java, it's more like an interface or type class. This choreop trait defines the signature of these operators, but it doesn't talk about how this object will be implemented. So in this setup, doing endpoint projection more or less means to construct a concrete choreop object for the current projection target and invoke this run method with it. So here's a simplified version of EPP in ChoRus. So this EPP and run method takes a choreography and construct what I call EPP op. And this is the specialized implementation of this choreop trait. In the locally operator, which is shown here, we compare the name of the specified location against the current projection target. If these two are the same, we execute the closure and wrap the return value inside this located value. Otherwise, we just return the placeholder value. So this is how EPP works in ChoRus, and other operators are implemented similarly. So this endpoint projection as implemented as dependency injection is a really general technique, and it should work with any programming language that supports high-order functions. That said, ChoRus does take advantage of Rust type system to provide more type-safe APIs. So in particular, as we saw earlier, ChoRus has the notion of type-level location set. Each choreography must have an associated set of locations, and ChoRus used that information to make sure that every location mentioned in the choreography is valid. And also, when you do EPP, we also check that the transport knows how to communicate with every other location that might be mentioned in the choreography. And this is implemented using this location set macro that is internally using type-level heterogeneous lists. So here is how this might be useful. So suppose that you define this hello world choreography, and you say that the Alice and Bob are the only location you can use in this choreography. But you might make a mistake, and you accidentally use Carol inside this choreography. In ChoRus, this is a type error. So if you're using Rust Analyzer or any other IDE plugins, it'll show up immediately as soon as you write this in the editor, which I think is really cool. Building on top of this is choreographic enclave operator, which offers a way to handle the knowledge of choice in a more fine-grained way. So as we saw, the broadcast operator sends the value to all locations, but not every location must know the value in all cases. If some locations are not affected by the choice, naive broadcast would add extra communication overhead. And also, depending on the value being shared, there could be possible security implications. The enclave operator executes a sub-choreography only at a subset of locations. And doing broadcast inside the sub-choreography will reach only to its participants. And ChoRus makes sure that the location set of the sub-choreography is indeed the subset of outer main choreography using the type-level location set. So that's about ChoRus. It has more features than I can discuss today. So if you're interested in any of these features listed here, please check out the ChoRus documentation or come talk to me later. I want to conclude the talk with some of the future research directions. I think library-level choreographic programming is still in its early stage. And there are a lot more research to be done from both practical and theoretical point of view. From practical point of view, I want to do large-scale evaluation and performance benchmarking, and hopefully doing so will reveal the advantages and disadvantages of this kind of approach. Also, encoding choreographic programming in a wider range of host languages with different characteristics will be interesting. So with EPPSDI, you should be able to implement choreographic programming library in your favorite language. And I want to see how the design of CP libraries will be affected by the host language features. From theoretical point of view, I'm interested in what kind of guarantees can we get out of library-level CP. And also, I want to see new ideas in theoretical CP research, such as how you deal with asynchrony and fault tolerance encoded at the library level. OK, so that's about it. So I presented ChoRus, which is a library-level choreographic programming implemented in the Rust language. So here's a link to the GitHub repo, which also has a link to the documentation. It would be great if you could leave a star on the GitHub. All right, thank you so much. That's it.
Thanks, Shun, for the interesting talk. I think we have time for a couple of questions. Let me run.
Just to connect also to your future work, what happens if so you are using a COM that is synchronous, so you are blocking the sender?
Exactly.
And what will happen if you are a mistake there? And currently, what do you think a programmer should do to handle communication errors? Communication errors? Yes.
Yeah, so we kind of assume there are no communication errors. So we provide basically no way of handling it. I don't know, but I feel like handling errors is difficult in choreographic programming in general. So I don't have really a good answer to that. But I would love to see what kind of approach there are and how we can encode that at the library level.
Thanks very much. This was a really interesting talk.
Thank you.
You have higher order choreographies, so I assume you have some way of being able to compose these. But with these type level location sets,
right.
When you do a broadcast, you're broadcasting to the locations in the set of the currently defined choreography.
Correct.
When you compose choreographies, does that broadcast now change to be, say, the union of the two, or how does that work?
Yeah, so when you compose choreographies, right, you have to make sure that the location set of the sub-choreography is a subset of the outer choreography. So and also this is this type level location set. You can think of it as a generics, right? So I guess the point is the location set can change when you compose choreographies. So I think I hope that answers the question.
Thanks again. I think we have time for a very quick question.
Very quick. Actually, I have two, but I will just stick to one.
You're losing time.
How much is it difficult to escape from the library. This is always something that worries me when I'm using a library. So the library imposes some restrictions, let's say, so that it works correctly.
Right.
But then, since it's a library, I can do something on the
Yes,
language.
exactly. So that is a great question, and there are a couple of ways you can get deadlocked, basically. So for example, if you use like shared mutable references with mutex in Rust, then you can get deadlocked. So our assumption is you don't use those advanced primitives, but I think it would be great if there could be something like a linter to make sure you don't accidentally use those dangerous features.
I think it's time to call the next speaker. Thanks again for
you.
the interesting talk.